The highlight of this lesson is about exponents. And the exponents is it can be a very effective way to work with big numbers. So during the class, we had students work as groups, like two students, say, in a group, to convert standard notations to scientific notations. As you can see, those numbers, they're pretty big with many, many zeros to trail. So what we did, we're going to, let's take a planet, say Mercury, and very much like review how we did and about scientific notation. Say, for instance, if I like to write Mercury, the average distance from the sun is going to be this number. Look at this. 1, 2, 3. That's it. 57,910,000,000 meters. So we're going to write this in scientific notation form. Remember, scientific notation form, we need to have, let's get this down a little bit, a times 10 to the some power. And the a must be a number that's between 10 and the 1. So therefore, this number, 57 billion something, we're gonna first locate that decimal. Well, where is the decimal, and then where would the decimal go? So let's make it bigger. Right now, the decimal is right here. Where do you want it to go? It's going to be between 5 and 7. And then we're going to count how many places it's going to travel. So 3 zeros as a group, that's a 3, 6, 9, 10 places. As the value of A, it should be 5.791 times 10 to the 10th power. So again, if we recall scientific notation, this is the form of scientific notation. And when we rewrite any number from a standard form to scientific notation, we need to locate, first of all, A. A is going to be a number between 1 and 10. At the beginning, here is where the decimal is at. And I wanted to go all the way between 5 and 7. So this is my A. Then I need to know how many places my decimal traveled. So 3 zeros as one group of 3, 6, 9, 10. That's how I get 10 to the 10th power. So with this idea, we can complete this table just as an exercise. Okay. So next, let's look at Venus and the average distance in meter. And this, we first got to locate A. And what would A be? And the A, at the moment, the decimal is right here. I want to go all the way between 1 and 0. So A is going to be 1.082 times 10 to the, how many places would the decimal travel? Again, we say a group of 3. So that's going to be 3, 6, 9, 10, 11. So 10 to the 11th power. And the next one, can you see this get same number of digits? So once I locate 1.496, my A is going to be 10 to the 11th power. And the next one is going to be very similar as 2.2794 times 10 to the 11th, 7.7833 times 10 to the 11th. Now I gain one more here. So A is going to be 1.4294 times 10 to the 12th. And next one is very similar as the previous in terms of the number of digits. A is going to be 2.87099 times 10 to the 12th power, 4.5043 times 10 to the 12th power. And this is how we converted all these big numbers into scientific notation form. So the next exercise, and so far everything is in terms of meters. And now we'd like to convert that into a kilometer. And we need to recall our unit conversion. So what about meter and a kilometer? And the conversion here is 1 kilometer get 1,000 meters in there, right? So now the question is, what if I have this many meters? How many kilometers in there? Or we can look at this form. So whichever form you feel comfortable with, this form, the scientific notation form, or the standard form. So the question is, how many 1,000 meters in each of those? And we're going to choose one to work with. Say, what if I choose this to work with? The question is how many 1,000 meter in there? And we should divide it by 1,000. If I divide it by 1,000, it's about removing the last 3 zeros. Once you divide it by 1,000, so I will have, as a scientific notation, what would you have? You still have the same digits as A, 5.791 times, you lost the 3 zeros, right? So it's going to be 10 to the 7th power. So the scientific notation in kilometer is going to be 5.791 times 10 to the 7th power. And the next one is very similar. A won't change. A 1.082 times 10 to the 8th, because we'll be losing 3 zeros when you divide it by 1,000. And the next one is going to be 1.496 times 10 to the 8th, and 2.2794 times 10 to the 8th, and 7.7833 times 10 to the 8th. Because this is all about dividing by 1,000 and you're losing 3 zeros. So if you count your place, that's going to be 3, 6, 8. And that's 10 to the 8th power. And the next few, and if we finish that, and we'll have 1.4294 times 10 to the what power now? Since we're going to divide it by 1,000, then I have 3, 6, 9. 9th power. And the next two are going to be very similar. A 7099 times 10 to the 9th, and 4.5043 times 10 to the 9th as the scientific notation in kilometer. And the next column, we like to know, okay, so what about if I like to convert the average distance from the sun into centimeter? Wow, centimeter is a very small measure, and if we recall the conversion, what about from meter to centimeter? 1 meter is 100 centimeter. So it's a question that we like to know how many 100 meters in this expression. How many 100 meters is about, let's divide by 100. When you divide it by 100, you actually lose 2 zeros at the end, don't you? If you lose 2 zeros, and your A is going to be the same, 5.791, and then we're going to go back to count places. Okay, let's go to write down our A as 5.791 times 10 to the what power? If I lose this last 2 zeros, I have a 1, that's a 4, 4 plus 3, that's going to be 7, and an 8. So it's going to be, oh, wait a second, sorry. No, I'm going to correct myself now, okay. I'm going to correct myself because we just said the idea here is 1 meter is 100 centimeter. We like to know how many centimeters in each. If 1 meter is 100 centimeters, I have a really huge number of some meters. So how many centimeters in there? We're supposed to multiply by 100. We're supposed to multiply by 100. So when we multiply by 100 on this given number, let's still use the first one. Okay, mercury. If we still use mercury, and the question is, okay, how this is so many meters. How many centimeters do I have? I need to multiply by 100. I need to multiply by 100. It really means I'm going to gain 2 zeros. I'm going to gain 2 zeros. Let's write it. Find a place to write this. Okay, I'm going to write it up here. So I will have a 5, 7, 9, 1, 0. And I have a 3 zeros, I have a 3 more zeros. This is the given form right now. This is what we have, right? If I multiply by 100, what's going to happen? Can you see we gain 2 more zeros? We're going to gain 2 more zeros, which we will have 5. We will have 5, 7, 9, 1. Let's count. We have a 3, 6, 7, 8, 9. I will have 9 zeros. So 1, 2, 3, 1, 2, 3, and one more group of 3. So this is supposed to be how many centimeters? This is how many centimeters. Now let's go to count. If I put commas in there, make it easier to count. So that's a group of 3, group of 3, group of 3, group of 3. So as A, we say stay as the same. You want decimal to go right now is here to there. So we go 3, 6, 9, 12. It's going to be the 12th power. And the next one, you have this number. Okay, you have this number. We read this number as 108 billion 200 million. And when you multiply by 100, it's about gaining 2 zeros. So as writing the scientific notation, they have the same value of A times 10 to the 13th power. And you can write them out this very similar way as I did earlier. So this will be the idea, okay? This will be the idea. What we try to, why do we work this out? Because we try to look at the relation in exponents. Look at this. What did I do from here to there? Didn't I multiply by 100? This is the scientific notation form of the standard form. If I multiply by 100, I'll get to here, right? What is 100? 100 is 10 to the second power. So if you multiply, let's move this over here. If you multiply 1.8 and 0.82 times 10 to the 11th, to the 11th, this is a number. I said if I multiply this by 100, which is 10 to the second, look what it becomes. It becomes 10 to the 13th. So what would you do between 11 and 2 to generate 13? You add them together. But that's because you have the same base. 10 is called base. So we have 1.0 and 1.082 times 13th power. And that is the point of what we're trying to indicate in exponent work. In any given exponent form, say 8 to the x, this 8 is called the base, and the x is called the exponent. So those are just the terms. Let's go back a little bit. And what about from meter to kilometer? Let's look at this one. I had this many meters, right? And I converted into this many kilometer. Or I had this many meters. I converted into this many kilometers. What did I do? I divided by 1,000. If I divide it by 1,000, I generate this number. What is 1,000? 1,000 is 10 to the third. So what we did, we had 4.5043 times 10 to the 12th divided by 10 to the third. Look what it becomes. It becomes ninth power. So what would you do between 3 and 12 to generate 9? You subtract them. So that's as a property we will introduce very soon. It's going to be more efficient if I just use the property in the exponent rather than doing it as a hard multiplication or division. So that's a 10 to the 12 minus 3, which is 9. So it's a 4.5043 times 10 to the 9th power, which is what we have here. So we did generate same solution, but this will get you there more efficient or quicker. Okay, let's go to our properties. And these are the set of properties. There are altogether 8. I know there are a lot, but really through practice, it helps you to remember them faster, easier to remember. And the first one and the first two are what we just indicated. When you have the same base, what would you do on the exponent? You add them. When you have the same base, when you divide two numbers, you subtract the exponent. This is a definition. X to the 0 is 1. We define that. And the distributive law, number 5 says a distributive law apply in exponent if you have x times y. Then you can write it as x to the a times y to the a. And there it goes with the division as well. So what if I have an exponent on the quotient of this number, then we can say it's going to be x to the a over y to the a. And number 4 is exponent on exponent. Try to understand this. What about 2 square to the third? What does that mean? Means I have the product of 2 square times itself, right? Then we just mentioned when you have them in multiplication, what would you do? You add the exponent, so you add 2, 2, 2 is going to be 2 to the 6. What do you do between 2 and the 3 to generate 6? You multiply them. So that explains this rule. These two are what we call the reciprocal, or dealing with a negative exponent. And we need to remember, whenever there is a negative exponent, it's about reciprocal, means you flip it. So this is a saying. Let's look at this. What if I have x to the negative 3? And this means it's going to be 1 over x to the third. At the moment, x to the negative 3 is really x to the negative 3 over 1. Between numerator and denominator, if you have a negative exponent, you just flip the whole term to the denominator. X to the negative 3 becomes 1 over x to the third. So on the other hand side, what if I have x to the negative 3 at the bottom? Then the exponent rule says, yeah, you can put it on the top. And meanwhile, you remove the negative exponent. You remove the negative sign. Negative exponent is really from here. What is x to the negative 1 is 1 over x. It doesn't make it a negative number. It stays whatever the number is, positive or negative of an x. This negative sign only means you're going to take the reciprocal. So let's look at a few problems from below here, and this is what we practice in class. So the first one says, what about 5 to the negative 2? And that goes with this property, number 7. He says it's 1 over 5 to the second. 5 to the second means 5 squared, and we just write it as 1 over 25. Okay, here is the next page. And all of them, we make use of the exponent rule. So for instance, we ask you to write as a positive exponent. So you're going to look through it. On x, there's a negative exponent. What about y? Y has a positive exponent. You don't have to worry about it. So what is x to the negative 2 is 1 over x to the second. So that's going to be 1 over x to the second times y to the third, which is y to the third over x squared as your final solution. Because y to the third can be written as y to the third over 1. When we multiply fractions, we multiply them straight across. And the next one, look at this, is also convert into positive exponent. So try to see where the negative exponent is in the denominator. So the numerator is fine. Keep the numerator. Denominator 1 over x to the negative 4 means x to the fourth. So x to the fourth. And you're done. Okay. So what about the next one? The next one, you get negative on both. So what if I have negative on both? The quickest way to look at this is about switching. So what if I have an x to the negative 1 over y to the negative 1? Then it's about switching sides. That's going to be y over x. So that's going to be y to the third over x to the fourth. And this one, in the denominator, look at this, y to the fourth square is going to be y to the eighth. That's your exponent rule at work. You multiply them together. So this is y to the eighth. And I have y to the negative 13 on top. What did we say about negative exponent? It's going to drop to the bottom. So it's going to be y to the 13th times y to the fourth. At the bottom, on top, I have 1 left. I have y to the 17th power as your final solution. And the next one, we also look for where is the negative exponent. It's right here, but you got to do a group at a time. So 3 is going to stay. You have x times y at the bottom. And this group is going to move to the bottom, x squared y to the negative 3 to the fourth power. Do one step at a time. And then recall xy to the eighth power was x to the a times y to the a, right? So when you have fourth power, and I will have xy times x squared to the fourth, which is x to the eighth. You multiply them together. And then y to the negative 3 to the fourth is going to be y to the negative 12. Okay, we're not quite done here because we still have a negative exponent. I do need to remove all the negative exponent, and therefore we are going to, can you see the only negative exponent item is right here, and this got to go upstairs. You got to go there. So I will have a 3 y to the 12th. I have x to the first, x to the 8th becomes x to the 9th times y. Now y to the 12th over y. Can you see these two? They have the same base. Therefore, we can subtract the exponent. I'll have 3y to the 12 minus 1 as 11 over x to the 9th. This is your final solution because now I don't have any negative exponent. And this next one, actually you're working with an actual number in scientific notation form, and we're going to see the benefit of using exponent properties, because if you do key in these numbers into the calculator, you probably run out of display. So that's why there's a benefit of learning the properties of exponent. Let's look at this. Multiplication is commute, so actually I can remove the parentheses. 3 times 10 to the 4th times 8 times 10 to the 9th. I just said multiplication is commute, so I can put the numbers together. 3 times 8. And now I'm looking at 10 to the 4th times 10 to the 9th. 10 as the base. They have same base. So it's going to be 10 to the 4 plus 9 as a 13. 3 times 8 is 24 times 10 to the 13th. This is really okay, but it would be better if you can write this in a scientific notation form, because it was given as a scientific notation form to begin with. So we can write this as 2.4 times 10 as 24 times 10 to the 13, and this will be 2.4 times 10 to the 1 13 is going to be 14th power as your final solution. And this last one, again, look for where you have a negative exponent is right here. So that got to go down. I have x to the 4th power squared, which is x to the 8th, times 4x to the 3rd. And again, we can use a distributive law. On the exponent, you have x to the 8th, 4 to the 3rd, x to the 3rd. They're all in relation of multiplication. And then we run out of space, kind of. Okay, let's make some room here. So I think I will write it here at the bottom, okay? And this will give me 1 over 4 to the 3rd is 64. X to the 8th times x to the 3rd is x to the 11th. X to the 11th, sorry. Let's not confuse with multiplication sign. So 1 over 64 times x to the 11th power as our final solution. 1 over 64 times x to the 11th power. That's our final solution.